refers to the bending of light as it passes through a medium.
Come again.
Refraction of light refers to the bending of light as it passes from one medium to another.
Gideon said this, but you are also, though you are correct, but you are lacking some key elements. What causes the bending? As a result of it being channeled through different media of different optical densities. Okay, Cephas, your hand was up as well. Okay, so the second definition can also be the change in the speed of light from one medium to another, also due to difference in optical densities of the pair of media of the media. And it can also be defined in terms of change in the wavelength of light as light moves from one medium into another of different optical densities. Is that okay? Okay, so we discussed this and then talked about when light moves from a less dense medium into a more dense medium, what happens? When light moves from a less dense medium into a more dense medium, how is the nature of the bending like? How is it? How does it bend? Yes, Francis.
It bends towards
It bends towards the normal. It bends towards the normal. 1, 2. 2. In terms of, say this in terms of the speed.
The speed reduces.
The speed of light reduces or decreases. What about the wavelength? What about the wavelength? What happens to the wavelength?
It reduces.
The wavelength also reduces. Don't forget, speed is directly proportional to wavelength. So meaning that if wavelength is reducing, then clearly if the speed is reducing, the wavelength would also reduce. Is that okay? All right. Now, what is Snell's law or states Snell's law? Let me call some of the ladies. Alidia. Ella, you also hear Yasmin. What, Yasmin, what is state Snell's law? Yasmin.
Yeah, light, sharp.
I'm listening. Anybody who is ready? Safas, your hand was up earlier. Safas.
Yeah. The Snell's law states that I can't really explain, but I can give a scenario. A ray of light travels from air into water. If the angle of incidence is 45 and the angle of refraction is 32, find the refractive evidence of index water.
Okay, so, okay, all right. Thank you, Safas, for your contribution. But some other, I think, hands are up. Let me. Ella Davis, Snell's law.
Please, no, please.
Ella, your line is breaking.
Please, can you hear me?
I can hear you now.
The Snell's law states that the ratio of the sine of angle of incidence to the sine of the angle of refraction is equal to a constant.
Hey, you are correct, but you are lacking some ingredients in your soup. Michelle.
Okay, please.
Okay, Ella, let Michelle also come in, okay? Michelle, I'm listening. Snell's law.
Snell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media.
For a given pair of media of different optical densities. Okay, for a given pair of media of different optical densities. The reason is that if the pair of media have the same densities, the light will not bend. It will travel straight. So it will only bend on condition that they have different optical densities. Okay. Now this constant is known as the what? The ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant for any given pair of media of different optical densities. This constant is known as the
Refractive index.
So what then is refractive index? When we say that the refractive index of glass is 1.5, what does it mean? If the refractive index of glass is said to be 1.5, what does it mean? Yes. We are recapping. Yes, Frank.
It means the sine of the angle of incidence over the sine of the angle of refraction is equal to 1.5.
Frank, I won't buy this. If this is a quiz, I'll give you 1 out of 3. The refractive index of glass is 1.5. What does it mean? Yes, Augustine. Elikam, you also hear.
Yes, sir.
The refractive index of glass is said to be 1.5. What does this statement mean?
Sir, please, it means that the speed of, sir, please, refractive index means it is the speed of light. Right. It's how much the speed of light is reduced when traveling through a medium compared to a vacuum.
So, Elikam, the refractive index of glass is 1.5. What does this statement actually mean?
Sir, please, it means it is the measure of the material's ability to bend light.
So what does it mean?
So it means glass can bend light 1.5 times as air.
Exactly. Okay, so refractive index basically refers to the measure of the material's ability to bend or deviate light. The measure of the material's ability to bend or deviate light. Please, are you writing?
Yes.
I gave you this last semester.
Sir, please, can you repeat yourself again?
The measure of the material's ability to bend or deviate light. The refractive index of a material is the measure of a material's ability to bend or deviate light. So if the refractive index of glass is said to be 1.5, then it means that glass can bend light 1.5 times as can be done by air. Don't forget here, this is absolute refractive index. Absolute refractive index. Glass can bend light 1.5 times as can be done by air. To also sound more professional. Please, 1.5 is the same as 150%. 1.5 is the same as 150%. So it means that glass can bend light 150% times as can be done by air. That's the meaning. Okay. What is the absolute refractive index of a material? Absolute refractive index of a material. What is absolute refractive index? Gideon.
So the absolute refractive index of a material is the material's ability to bend or reflect light when light passes through it.
When light
passes through the material. When light passes through the material.
You are not wrong, but you are not hitting the nail on the head. Somebody else, please go ahead.
Sir, please. Absolute refractive index of a medium is defined as the ratio of the speed of light in a vacuum to the speed of light in the specific medium.
Okay. So you said ratio of the speed of light in vacuum or air. Okay. Or air to a specific medium. So basically, when we talk about absolute refractive index, I told you that absolute refractive index is the actual or the real refractive index of a material when light moves from air into a given material. Okay. So for absolute refractive index is the refractive index of a material when light moves from air or vacuum into a material. It's a must that whenever we talk about absolute refractive index, light must first move from air into a certain given material. If it is the other way around, the light propagated from a material to air, it is referred to as what? If it is the other way around, from the material to air, this is referred to as, hey, you people have forgotten, no? It is reversed
refractive index.
Reversed refractive index. And the absolute refractive index of a material can be expressed using deviation from air into the medium or change in the speed. So absolute refractive index, the symbol N or mu can be sine of, using Snell's law, sine I over sine of R, where I is the angle of incidence and R is the angle of what? Refraction. This can also be the ratio of the speed of light, in air or vacuum over the speed of light in a medium. This is also equal to ratio of wavelength of light in air and wavelength of light in a given material or medium. So please take note of these stuff. Okay. Now we express Snell's law as sine I on sine R. Don't forget, Snell's law can also be expressed as the refractive index of air times the sine of the angle of incidence in air, which is also equal to the refractive index of a given medium times the sine of the angle of refraction in the medium. So this This is also the same as Snell's law. Are you with me? Hello, are you with me?
Yes, sir.
Yes, sir.
Okay. Then we talked about total internal reflection. Total internal reflection. What is total internal reflection? Class, what is total internal reflection? TIR. Anybody to help? Anybody to help? We are revising in order to also help those who have just joined. What is total internal reflection? Yes, Frank, your hand is up.
Is when a ray of light refracts from a more dense medium to a less dense medium and rather reflects at an angle greater than 90 degrees.
Okay, it makes some sense. Michelle, come into
Okay,
total
please.
internal reflection.
It's when a light ray traveling from a denser medium to a less dense medium is completely reflected back into the denser medium instead of refracting out. Sorry. Yes, that's what I.
Okay. The last contribution, Gideon.
It is when light is traveling from a dense medium into a more denser medium is completely or totally refracted, where the angle of incidence in the dense medium is greater than the critical angle of the denser medium.
All right. Now, Ella, let's discuss something. Let's discuss conditions for total internal reflection to occur. What are the conditions necessary or that must prevail for total internal reflection to occur? Ella, let's hear from Ella. Just give us one of the conditions. Ella Davis. Yasmin. Yasmin. Okay, Alitia, go ahead. Yasmin, let's hear from Alitia. Then Akumi.
Yes, one is light must travel from a more dense medium to a less dense medium.
Good. So light must travel from must travel from a more dense medium to a less dense medium. Good. When you understand the conditions, then you can put them together to make your point. Yes, two. What is the second condition? Okay, Yasmin, noted. Okay. What's the second condition for total internal reflection to occur? Yes, Frank, let me call Elikem.
So please, the angle of incidence must be greater than the critical angle for the two
So
medium.
two, angle of, thank you, angle of incidence must be greater than the critical angle of the material. Good. So the critical angle of the material. These are the three conditions, two conditions for total internal reflection to occur. So let's quickly.
So please, are they the only conditions for internal reflection?
Total internal reflection.
They are the only conditions.
Yes.
Okay.
So if let's have an interface or a boundary separating these two material. This is the first one is glass, and the second one air. It can be any two different material as well. So, but the important thing is that the light must come from a denser medium to a less dense medium. So it means it can be water, air. It can be, it can also be water and then cooking oil. Okay. Let's draw a vertical line to represent the normal. So if there's the normal, when light incidence at an angle, so this is the incident ray. This is the angle of incidence. Now, once the light is moving from glass to air, of course, the refracted ray will bend away from the normal. So, as we increase the angle of incidence in the denser medium, a point will be reached where the angle of the refracted ray will lie just on the boundary. Okay. And it means at that point, the angle of refraction will be 90 degrees. So that angle of incidence, which produces an angle of refraction of 90, is what we are calling as the critical angle. So when the angle of refraction is 90, the angle of incidence is equal to the critical angle of the material. Okay, so critical angle refers to that angle of incidence in a more dense medium, which results in an angle of refraction of 90 degrees in the less dense medium. Please, did you get that?
No.
No, please.
The critical angle is defined as the angle of incidence in the less dense medium that results in an angle of refraction of 90 degrees in the less dense medium.
Please, can you take it again by a little bit slowly?
Okay, so the critical angle is the angle of incidence, in the more dense medium, the angle of incidence in the more dense medium that results in an angle of refraction of 90 degrees in the less dense medium. That results in an angle of refraction of 90 degrees in the less dense medium. Okay. Or it can also be defined as this. If you are asked to explain the critical angle of a material, The critical angle of a material is that angle of incidence in the more dense medium that produces an angle of refraction of 90. That produces an angle of refraction of 90 degrees in the less dense medium. Are you okay? Class, are you okay?
Yes, sir.
Yes, please.
So what then is total internal reflection? Total internal reflection, I'm going through it after that take my time to give you the definition. Total internal reflection is defined as, or is the phenomenon whereby when light moves from a more dense medium to a less dense medium, is a phenomenon whereby when light moves from a more dense medium to a less dense medium, and the angle of incidence in the more dense medium is greater than the critical angle, and the angle of incidence in the more dense medium is greater than the critical angle of the material, the incident light is completely or totally reflected. Is a phenomenon whereby when light moves from a more dense medium into a less dense medium, and the angle of incidence in the dense medium is greater than the critical angle of the material, and the angle of incidence in the dense medium or more dense medium is greater than the critical angle of the material, the incident light is totally or completely reflected. Please, are we okay?
Yes, sir.
The incident light is completely or totally reflected. Please, if you have any question, quickly ask and let's continue. Okay, so what it means is that to be able to tell or to be able to effect total internal reflection in a material, one of the key things you must know is that you must know the critical angle of the material. To cause total internal reflection to occur in a material, one of the requirements is that you must first know the critical angle of the material. Okay, so we are going to look at how we can determine the critical angle of the dense or the denser medium, because that's the requirement for total internal reflection to occur in a material. Class, are you okay?
Yes, sir.
So as an engineer, maybe you are given fiberglass or glass. Let me take attendance, okay? I'll be with you in a minute or two. Who is using my board? Okay, so we can continue. So as an engineer, you are given a material and you want to cause total internal reflection within the material. So how do we figure out or determine the critical angle? Because you can only do that, cause total internal reflection in the material, when you know the critical angle of the material. So let's assume that, yes, as we said, the dense medium is glass. Let's assume the absolute refractive index of glass is mu G, and then the absolute refractive index of air is mu A. Okay, so Snell's law says that the product of the refractive index and the sine of the angle of incidence in the first medium, which is glass, must be equal to the product of the refractive index of the less dense medium, which in this case is air, and the sine of the angle of refraction in air, which is 90. Don't forget, we are at the critical angle. So at this point, the angle of incidence I is equal to, can be named as C. So let's make sine C the subject. Sine C in this case is equal to refractive index of air times 90. Sine 90 is 1. So times 1 divided by the refractive index of glass. So it means that sine C is simply equal to, once the less dense medium is air, okay, once the less dense medium is air, the refractive index of air and vacuum is 1. So we have 1 times 1 divided by the refractive index of glass. The refractive index of glass. So this is equal to 1 over mu of glass. Therefore, C would be equal to sine inverse of 1 over the absolute refractive index of glass. So this is how we can determine the critical angle of glass. Once we know the absolute refractive index of glass, we can easily use that to calculate the critical angle. And once we determine the critical angle of the more dense medium, we can easily determine cause total internal reflection. Because for total internal reflection to occur, the angle of incidence must be greater than the critical angle of the material. Please, is there any question? Is there any question? So this is it about total internal reflection and how to determine the critical angle and subsequently cause total internal reflection to occur in a given material. If there is no question, let's talk about applications of total internal reflection. Gideon, your hand is up.
So we can explain the part where the mu G became the M.
Mu, you see, absolute refractive index can be represented as mu or nu, which looks like n. So I just changed mu to n because that is what most books use. In most books, you see sine C to be equal to 1 over nu or n, where n is the absolute refractive index of the dense medium. It can also be sine C is equal to 1 over mu. Okay, so I'm just using the symbols for absolute refractive index. Gideon, are you okay?
Yes, sir, please, thank you.
Joshua,
Please, is that the formula for calculating the critical angle?
exactly, of the material, but you have asked a good question. So sine C is equal to 1 over the absolute refractive index of the material. So that if you are looking for C, it will be equal to the sine inverse of 1 over the absolute refractive index of the dense medium. Now, take note that you can only use this formula when the less dense medium is air. The less dense or the rare medium is air. Okay. If the less dense medium is not air, please, it is mu of glass times sine I is equal to mu of the rare medium times sine of 90. So that once the angle of refraction is 90, then it means I is equal to the critical angle. So mu G times sine C is equal to mu R. Sine 90 is 1. Okay. Therefore, sine C is equal to the ratio of the refractive index of the less dense medium to the refractive index index of the more dense medium, which is glass. So if the less dense medium is not air, this is the formula to use in determining the critical angle of the more dense medium. Okay, so please get the difference. This is when the less dense medium is air, and this is when the less dense medium is not air. Are we okay? Class, are we okay?
Yes, sir. Sir,
Yes, sir.
Hello?
please, when you're done, the diagram, I couldn't really see it. So please, when you're done, I would like to copy it again.
Okay, this is it.
Thank you, sir.
All right, so please quickly do that. When you finish, let me know so we can continue. The next is applications of total internal reflection.
Sir, please, where you've written sine C is equal to UA times 1 over.
Sine, is it this part?
No, where under the key, where the key is.
Where the
Key, like beneath the key.
is it sine C is equal to 1 over
No,
n?
UA times 1.
Oh, okay,
Yeah.
over mu of glass, the absolute refractive index of glass. There's a sine C is equal to UA, which is the refractive index of glass of air over the refractive index of glass G. Are you okay?
Yes, please.
Where did you put the keys?
Can I continue?
You can't.
Sir, please, I'm almost done. A few seconds.
You're asking me where is the key. I'm mad. You send the key to school. Are you
Sir, please, I'm
okay? You
done.
don't lock the door.
Please mute yourself. Who is here?
You see how we suffer before we
Oh,
see how.
else everything will come to the classroom. Let me mute all so that if you want to talk, you come in, okay? Applications of total internal reflection. Applications of total internal reflection of TIR. Yes. If you are used to some applications of TIR, please share it with me or with the class. Elikem, your hand is up.
Formation of mirage.
Good. 1. In the formation of mirage. Please, you know what a mirage is?
Yes, sir.
Yes,
What is
please.
it? What is it? Ernest, can you tell us what is a mirage? Or
Sir, please.
oh, you
Um,
have no
no,
you
I
have no
think
idea.
I can explain. I think I can.
Uh-huh.
Mirage is an optical illusion which occurs when light travels from a cooler, denser air into a hotter, less dense air, causing it to bend upwards, which creates that illusion that you're seeing water.
So yes, you are right, but let's go practical so that all of us can understand what mirage is. You are giving me the physics or the scientific formation of mirage, but what is it? Just explanation. Gideon. Hello, Gideon.
It is when you're driving on the road, like
Uh-huh.
and you look ahead of you, you see like water on the road, but when you get closer, it's like there's nothing there. That is a mirage.
Exactly. You see, so usually whenever you drive um, on sunny afternoons, okay, or even when you walk during sunny afternoon and you look ahead, it always appears as if there is a pool of water on the surface of the road. You walk, and you will never catch this. You will never see it. As you go by, it also goes further. Okay. So that optical illusion or seemingly appearance of that pool of water on the road is what we call as mirage. It also occurs on the desert. Those who have um, uh, taken a sojourn or have traveled on the desert, you see, on the desert because of the temperature, there is no water. So when travelers walk and then they look ahead, it always appears as if there is some water, pool of water ahead of them. Because of thirst and the desire to quench their thirst, they run to just, drink the water. And as they walk or run closer, that apparent pool also goes further. They will never catch it. So that is a mirage. And it occurs during hot, sunny afternoons, not cold, no, or low temperature situations. All right, so that is it. One of the applications is formation of mirage. 2, applications of total internal reflection. 2,
Sir,
Nana Kumi,
And please, fish eye view.
come again.
Fish eye view.
The fish eye view. Yes, the fish eye view. Fishes in a water body do not need to turn to see. Especially, let me give a quick. This is the surface of the water. Assuming this is a fish. And then fishes, an object is here. Fishes can easily see without turning to look at it because light from the object will just travel, hit the boundary, and then because of total internal reflection, will just reflect into the eye of the fish. So they can easily see obstacles, predators, without actually turning.
Flavor.
Okay.
You want to give me flavor? No, I mean like I'm getting like I need a little flavor.
Please mute yourself if
But
you are
flavor
not.
of
Hello. The
flavor.
favors must be over. Favors must be over. Okay. So that's a fish eye view. Ernest.
Sir, please, an example is optical fibers for telecommunication.
Good. It is also used in fiber communication. Used in fiber
Sorry, but I
optics.
don't actually have any money right
So
now.
please, I have a question.
I'm coming in. Fiber optics. In telecommunication.
I'm going to sign up around to on this later. Sorry.
Zoom user, whatever you are saying can be heard here, please. So please mute yourself, okay? Gideon. Gideon, go ahead with your question. Hello, Gideon.
So this how come the light is traveling from beneath the water?
I'm looking at an object here. If there's an object here, you see, we see as a result of light coming from us. So if there is an object here, okay, light from the object will just hit on the interface and then reflect to the eye of the fish. Gideon, are you okay? It's not actually light or torchlight, but an object here, okay, can easily be seen because ray of light from the object will be originated from the object and then be incidented on the interface and then reflect into the eye of the fish. That's what I'm saying.
Okay, sir. Thank you.
Then fiber optic communication. You see, before the invention of fiber optics, long distance or telecommunication was done by satellite. And so if you are in Ghana and you want to talk to, if you are in Ghana and you want to talk to somebody abroad, your call, when you dial, the signal must go to the nearest MTN, Vodafone, now Telecel, and then other network providers must in the community. You also go to their telecommunication office in Accra. Then when the call is going outside Ghana, it will be sent to satellite station in Kuntunsi around Amasaman area. Before the call is given to a satellite in space, okay? When it goes to the satellite in space, because it's an international call, your call must go to US. And this is the reason why usually when you are calling somebody in Togo, it is more expensive than calling somebody in US. Please, are you listening? Hello, class, are you there?
Yeah.
So This is the reason why calling somebody in Togo, Cote d'Ivoire, Burkina Faso is more expensive than calling somebody in US because of this route through which your call must go. Meaning, if you are calling somebody in Togo, before your call must go to US before it comes back to Togo. Meanwhile, if it's US, we'll just go there and that's it. Okay. Now, there is optical fiber use, which is a cable, a glass tube cable, which is laid through the sea to UK, to US. So when you call in Ghana, your call will just travel through the fiber cable and go to UK direct without going to space. If you remember, there was a time where internet service was disrupted for about 2 weeks, and we're told that I think the fiber cable which transmits data was broken. Please, did you hear that?
Yes, yes, please. It
Yes,
was
sir.
So
it was rumored that a shark came to wander
yes,
and linger around the
exactly.
cables.
Exactly. And sometimes to ships,
Yes.
you see, it is guided, but ships can also sail around and then destroy the cable. It is actually laid on seabed. It is actually laid on the seabed. Okay. So the fiber cable is a bundle of glass tube, which is laid from countries to countries to provide internet data. And it has its own advantages. One of the advantages is that vast amounts of information can be transmitted over fiber cable than using copper wire. So the advantages of fiber optic communication is that large or vast amounts of data or voice calls can be transmitted over fiber communication than copper wire. And because the information is sent in a form of light, the speed is so much enhanced than it propagated on copper wires. Please, are you noting down the advantages of fiber optic communication over the wire? The first one is that large amounts of information and data can be transmitted over fiber optics than copper wire. Please, you have that?
Yes, sir.
Okay. 2, the speed of propagation is so much enhanced. Speed of propagation is so much enhanced compared to copper wire or coaxial wires or cables compared to copper wire. This is because, you see, the data travels at the speed of light. So propagation speed is greater than in wires. Frank?
Sir, please, can you repeat the second point?
So the speed of transmission or propagation is so much enhanced as compared to speed of transmission on wires. The speed of
Sir,
transmission. Hello?
please, if we also have our advantages, can we write them down?
Yes. Yes. I'll give you 3, but you must share what you have with me to confirm, okay?
Okay.
Then the third advantage is that crosstalk crosstalk is eliminated. Is eliminated in fiber communication. What is crosstalk? I once worked as a student trainee in Ghana Telecom, then Ghana Telecom. I was on the landline when a call suddenly came from nowhere. I was talking to somebody, but somebody's call also entered